Light can also change its direction by a process known as refraction. We stated before that light travels in a vacuum at a speed of 3.00 times 10 to the 8th meters per second. However, in a clear substance or medium such as air, water, glass, or plastic, light travels much slower. The light is slowed because it is continually absorbed and remitted by the molecules in the medium. How much the light is slowed is described by the index of refraction, a unitless number abbreviated as n. This is just the speed of light in a vacuum divided by the speed of light in the given medium. Suppose the speed of light in a certain medium is only 2.00 times 10 to the 8 meters per second. What is the index of refraction of that medium? Correct. The exponent and units cancel, and 3 divided by 2 is 1.5. When the speed of light is slowed by a medium, it is the wavelength that changes, not the frequency. As a result, the index of refraction is also a relationship between the wavelength of light in a vacuum and in a medium. This was used in the previous section while studying thin films. When a light ray passes at an angle from one medium to another with a different index of refraction, it must change its direction. Similarly, when light travels from a faster medium to a slower medium, it turns closer to the normal. The wave picture can help to understand this. In the slower medium, the wave fronts are closer together. In order for the wave fronts to match up at the interface, the ray must be at a steeper angle. The angle between the incoming light ray and the normal is again called the angle of incidence. The angle for the outgoing ray is the angle of refraction. Often these are just referred to as θ1 and θ2. The relationship between these angles is given by Snell's law, which states that the index of refraction in medium 1 times the sine of the angle in medium 1 equals the index of refraction in medium 2 times the sine of the angle in medium 2, or n1 sine θ1 equals n2 sine θ2. In any real situation, not all of the light will enter the new medium. Some of the light will be reflected at the interface. Suppose light in air, n equals 1.0, reaches an interface with glass, n equals 1.5, at an angle of 50 degrees. What is the angle of the refracted light? Correct. We do this problem by solving Snell's law for angle 2 and inserting the numbers. What is the angle of the reflected ray? Correct. The angle of reflection equals the angle of incidence. Now what happens if we begin with the light in the glass and have it hit incident on the air at 50 degrees? Repeat the calculation and see what happens. Your calculator should have given you an error message. The sine of angle 2 would have to be greater than 1 to get out of the glass, and that is impossible. In this case, all of the light is reflected inside the glass.